Welcome in Book Explained YouTube channel. Today, we're diving into an absolute giant of a book, Stephen Hawking's A Brief History of Time. This isn't just a book about physics, it's a story about our relentless quest to understand the universe itself, and it forces us to confront the biggest questions we could ever possibly ask. And these are the questions, right here, that sit at the very heart of the book. I mean, these are the questions we've been asking for thousands of years, just staring up at the night sky. What Hawking did so brilliantly was to chart the incredible evolution of our answers, from ancient myths all the way to the bleeding edge of modern physics. And that's the journey we're going to take today, following the path that he laid out for us.
So, to really get a grip on where we are now, we have to look back at where we started. And for most of human history, our picture of the universe, well, it was built on stories and what just felt right.
Hawking kicks things off with this fantastic story. A scientist is giving a lecture on astronomy, and this old lady stands up and says, "That's all wrong. The world is a flat plate sitting on the back of a giant tortoise." So the scientist, a bit smug, asks her, "Well, what is the tortoise standing on?" And she replies, "You're very clever, young man, but it's turtles all the way down." Now, as funny as that sounds, it makes a brilliant point. We have always created models to try and make sense of the cosmos around us.
But hey, our models weren't always just myths and legends. Way back in 340 BC, the Greek philosopher Aristotle used actual real-world evidence to argue that the Earth was a sphere. He pointed to things anyone could go out and see for themselves. The Earth's shadow during a lunar eclipse is always round, the North Star sits lower in the sky the further south you travel, and when you watch a ship approach from the sea, you see its sails long before you see its hull. This wasn't mythology, this was the birth of real scientific reasoning.
So Aristotle was spot on about the spherical Earth, but he also thought it was sitting perfectly still, right at the center of everything. This idea was later fleshed out and formalized by the astronomer Ptolemy. And his model, with the sun, the moon, the planets, all of it revolving around the Earth, became the accepted truth for an almost unbelievable 1,500 years.
For 1,500 years, that Earth-centered universe was rock solid. But then, a series of revolutionary ideas started to chip away at it, piece by piece, building a completely new picture of reality.
The very first crack in this ancient model showed up in 1514. A Polish priest, Nicholas Copernicus, came up with a much simpler but deeply radical idea, and he was so afraid of what the church might think that he actually circulated it anonymously at first.
Copernicus proposed a total shift in perspective. What if we put the sun at the center instead of the Earth? As you can see here, the old Ptolemaic model had to invent these incredibly complicated paths just to make the math work. The Copernican model was way simpler, more elegant, and so revolutionary that for about a century it was basically ignored.
And then the evidence just started pouring in. In 1609, Galileo pointed his brand new telescope at Jupiter and saw moons orbiting it, which was clear proof that not everything in the sky revolves around the Earth. That same year, Johannes Kepler figured out that planets move in ellipses, not perfect circles. But the final knockout punch, that came from Sir Isaac Newton.
In 1687, Newton published his law of universal gravitation. Just think about that. It was a single, beautiful equation that could explain everything from an apple falling to the orbit of the moon. For the first time, we had a physical law that governed the heavens. It described the universe as this predictable, mechanical, almost clockwork machine. And it also meant that the universe had to be infinite.
So Newton's infinite, clockwork universe. It seemed perfect. But as people thought about it more and more, they realized it had some pretty deep, unsettling problems hiding inside it.
So this first question even stumped Newton himself. In an infinite space with infinite stars all pulling on each other, what stops the whole thing from just collapsing into one giant cosmic clump? Newton kind of argued that in an infinite space there's no center to fall to, but that's like trying to balance a million pencils on their tips at once. The slightest nudge would send the whole thing tumbling down. It was incredibly unstable.
And this second paradox, this one is a real mind-bender. It's known as Olber's paradox, and it goes like this. If the universe is infinite and it's been around forever and it's full of stars, then no matter where you look, your line of sight should eventually end on a star. The entire night sky should be as bright as the surface of the sun. So the simple fact that it gets dark at night tells us something is fundamentally wrong with our picture of an infinite, static, eternal universe.
For more than 200 years, these paradoxes just sat there, completely unsolved. The answers, when they finally came, wouldn't just tweak our model of the universe, they were going to blow it wide open.
The game-changing discovery came from an American astronomer.
Edwin Hubble. From his perch at the Mount Wilson Observatory, he was looking at distant galaxies, and he noticed something absolutely extraordinary. Hubble saw that light from these distant galaxies was stretched out, or redshifted, which means they were all flying away from us. And he found a clear pattern. The farther away a galaxy was, the faster it was speeding away. The universe wasn't static at all, it was expanding. And this one observation solved both of those old paradoxes in a single stroke. The universe isn't collapsing because it's flying apart, and the night sky is dark because the light from the most distant stars just hasn't had time to reach us yet. Now just stop and think about the implication of that for a second. If you hit the rewind button on an expanding universe, everything gets closer and closer and closer together. The only logical conclusion is that everything, all matter, all energy, space itself, must have started from a single, unimaginably hot and dense point. This moment eventually got a name, the Big Bang.
And what's wild is that the math for this already existed. A Russian physicist named Alexander Friedman had already used Einstein's theory of general relativity to work it out. His models showed two main possibilities for the universe's ultimate fate. It all comes down to its density. If there's not enough matter, not enough gravity, it'll just keep expanding forever. But if there is enough matter to hit a certain critical density, gravity will eventually win the cosmic tug-of-war, stop the expansion, and pull everything back together in what's known as the Big Crunch.
The Big Bang Theory was a monumental achievement. It explained our observations and it gave our universe a history. But it also pointed to a moment where our understanding of physics completely and utterly breaks down. You see, right at the instant of the Big Bang, the theory predicts a singularity, a point of infinite density and infinite temperature, where space and time just cease to exist. But whenever you see the word infinity in physics, it's basically a giant red flag telling you that your theory is failing. As Hawking explains it, general relativity actually predicts its own downfall. It tells us that to really understand the origin of the universe, we're going to need a new theory, one that can unite gravity with quantum mechanics. And this brings us to one of Hawking's own profound ideas, the no-boundary proposal. He suggested that if we could finally unite gravity and quantum mechanics, that singularity, that sharp point of creation, might just disappear. The universe could be finite in time, but have no beginning or end, kind of like the surface of the Earth. The Earth is finite, right? But there's no edge you can fall off of. In this view, asking what came before the Big Bang is like standing at the North Pole and asking, what's north of here? The question itself doesn't make sense. The implications of this are just staggering. If the universe has no boundary, it doesn't need a moment of creation. It doesn't need a cause to set it all in motion. It just is, completely self-contained and governed by the laws of science. This idea suggests that the entire universe could have naturally emerged from nothing, with tiny quantum fluctuations at the beginning getting stretched by rapid expansion to form all the galaxies and stars we see today. And this brings us right back to the ultimate question. Even if we find a complete, unified theory, a single set of equations that describes a self-contained universe, Hawking leaves us with one final profound mystery. A theory is just a set of rules. An equation is just an equation. So why is there a universe for those rules to govern in the first place? Why does the universe go to all the bother of existing? And that's a question that might just push beyond the limits of science itself, leaving us all to wonder.